SwayamPrabha. Digital India. Educated India.
Morning. So welcome back after that 1 week break. So I've written down some schedules on the blackboard. Tomorrow is a public holiday in Tamil Nadu, so we are having the general elections for Tamil Nadu Legislative Assembly. So it's a government holiday. So there's no class tomorrow. Since this is the last week in respect of my classes, I want to take these 3 classes. So this week you'll have Monday, Wednesday, and Thursday, right? Today's class anyway is there. Tomorrow, instead of tomorrow, I'm going to take Thursday, 12:55 to 1:50 p.m. I'm not taking at 12 o'clock because I have 11 to 12 class. Atmospherics, it will be very difficult to switch over immediately and suppose that overshoots. Okay. Please note that the quiz also is on a Thursday, but the time will be 12 o'clock. Okay, for the quiz, 29th April. So you'll get sufficient notice. So please don't. The quiz is only for 50 minutes. If you anticipate any trouble, you should send an email to us. Answer sheet by 1:50, not at 1:35 saying that this is okay, that is not working, because the quiz is only for 50 minutes. Okay. Number 1. Number 2, please don't send an email to me. I already told you I've got thousands of mails in my inbox. Since it is course related, send it to Akala, Rajesh, and Suraj. If you want a copy to me, I should not be the primary recipient of the email. Okay. So the best strategy would be finish it in 50 minutes and try to upload by 1 o'clock itself. If you want 5-10 minutes revise, and if there is a problem, we need to get your email before 1:30. 1:30, you should not, whatever be the experiment, you should not say, I tried, this is not working, that is not working. Therefore, I send an email. That exercise you should do between 12:50 and 1:30. You're not supposed to do that exercise at 1:30. First quiz, sometimes we permitted. Now we are not going to permit because the quiz itself is only for 50 minutes. All right. So please remember this. All right. And worst case, you send an email before 1:30. The mail should have been, or the origin of the mail should be before 13:30 hours. Okay. Send it to, so all that will be clear in the paper. Okay. Already we finished the first quiz and you got the answers, answer sheets, the graded ones. Assignment test 1 correction is, assignment test 2 correction is going on. Assignment test 1 also we have finished. So already 30% is over. This will be 20%, and end sum will have a similar pattern, except that it will be split to morning and afternoon. So you'll have 2 hours in the morning and half an hour for upload. Then there will be lunch break, and then afternoon will be neural networks. Okay. It will be on the day of the D slot exam, which is as of now the end sem will be 19th May. Okay, D slot. Okay, so it will be in the regular D slot of the institute. But we'll follow the same method instead of just going to Kendra Vidyalaya, this all that we don't. We'll follow this method. So it will be user specific questions and so on. All right. So please note this. Okay. Instead of tomorrow, we'll meet on Thursday, but Wednesday's class will be there as usual. So the subject of Bayesian methods will be completed in the 3 classes. Okay. So this Bayesian method basically brings in some new flavor. Okay. This whole subject of inverse heat transfer. So it basically originates from the Bayes theorem. Okay. So the Bayes theorem is after Reverend Thomas Bayes. I'm just checking the when he lived. Okay. After Thomas Bayes, a philosopher, mathematician, and all that. 1701 to 1761. Okay, so he's an English philosopher. Okay, as the name suggests, he's an English philosopher as well as mathematician. He introduced us to the ideas of conditional probability. The probability of A being true. Okay, if A and B are two events, the probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. Okay. Is it okay? For example, probability of somebody getting a COVID or something is A. Probability of somebody being a smoker is B. What is the probability of what is the probability that if you're a smoker you will get COVID? I mean, it is just kind of what is, so it should have higher probability compared to the general population. So it is like that. Okay. So what is the probability of somebody getting a heart attack? What is the probability of somebody already having diabetes in the general population? What is the probability of somebody with diabetes getting a heart attack or something? Okay. Over 10 year, 20 year, 30 year, whatever be your period. So A and B, P is the probability. This is equation number 1. So this is basically the Bayes theorem. I think it is Bayes' theorem. This is the probability. Okay. So in equation 1, A and B are events. Okay. Needless to say, P of B cannot be 0. Otherwise, the whole thing will come. P of B cannot be 0. Otherwise, the whole thing will come. Okay. P of A given B is a conditional probability.
Should be of A intersection B, no, sir, in numerator. Expression for P of A given B is P of A intersection B by P of B, no, sir. You wrote something, just P of A.
I don't understand what you're saying.
Sir,
Who is this?
Sai Kumar.
Tell me, Sai.
Sir, P of A given B is P of A intersection B.
No, A intersection. A intersection is all high school stuff. Let's leave all the A. There's no A intersection. We'll say A given B. This is the nomenclature. Okay. There is no intersection and all that in this. That is not the nomenclature we follow. This is A given B. I'll write what it is. I'll explain. Intersection, union, Venn diagram, all that is over. Okay, this is Bayes' theorem. All right. So is a conditional. So this is the likelihood of please note, sorry, likelihood of A happening when B is true. That is what we are saying. It is quite different from what we are saying. What is the probability of A happening when B is true? Okay. All right. So P of B given A is likelihood of B occurring when A is true. Okay, so this is called conditional probability. So the idea of conditional probability is introduced in the Bayesian method. Okay, so from the Bayes theorem, you must have studied orange balls, yellow balls, black balls, blah blah blah, whatever. So we will develop on these concepts and try to see how to use it in the inverse problem. That is the whole idea of the Bayesian method. Once I introduce what that prior is, you will understand this a little more clearly. A and B are independent of each other. That means A and B are occurring independent of each other. Okay, so this PA and PB in statistics terminology, in probability and statistics, they are called marginal probabilities. Okay, Sai, to answer your question, it is not intersection and all that. For example, let us say there is a slab and you've got 5 temperatures, you measured. Okay. What is the probability? For example, what is the probability of getting T1 for a particular value of K? What is the probability of T2 for a given value of K? For example, what is the probability of T1 Tn for a given value of K? We are looking at this. There's intersection B, union B, all that is for writing exams and this thing. We are going to engineering. Okay. So there are a couple of measurements. What is the probability? If you assume a particular value of K, you will get this temperature. We want the ulta actually. We want the ulta of this. What is the probability that this K caused all this? So that is what we are trying to do. All right. Because what we have is measurements. What we have is the effect. From the effect, we are trying to get the cause. But we are trying to go to the root of this. That is why we say there is a conditional probability. What is the conditional probability of getting T1, T2, T3, T4, T5, T6, T7, T8, T8, T9, T10 in a slab? Okay. For an assumed value of K or an assumed value of heat flux. Is that okay? So what we can do now is we can assume different values of thermal conductivity, solve the forward model, get these temperatures, and put all the probabilities into e to the power of minus some chi square, where that chi square is basically sigma I equal to 1 to n Ri square residual. So we bring in the residual, which is basically e to the power of minus kappa square of the simulated and observed, and that is the way we are progressing towards engineering. But we start from elementary concepts and then we go to advanced concepts. Okay. So, but the basis for this is the Bayesian, is the Bayes theorem. Okay. So, all right. So these are the. So this is the preliminary.
Sir.
Okay.
Sir, so what do you mean by that A and B are occurring independent of each other?
They are independent events. That is the way we define what occurring in. That is the way. That is the nomenclature.
Sir, if A and B are independent, then P A even B will be equal to PA only, right? Like B won't affect A.
No. You don't get into the circular arguments. What I'm saying is, by knowing PA, you cannot find PB. That's what I'm saying.
Oh, okay, sir.
So
yeah, understood.
Understood. Please understand it carefully. By knowing PA, if you get PB, there is no inverse problem at all. Okay. So we have to be very clear. You have to grow out of your basic algebra which somebody has taught. Okay, that is important. But so that is what I meant by this. Okay. Of course, temperature and thermal conductivity are related. Okay. So now, so with this we can proceed to solve the inverse problem. But before that, let us solve some simple problems. Okay. So in fact, to bring things to context, we can use the Bayes theorem like this. Okay. So this is the Bayes theorem for continuous variables. Okay. So please note this. The P of x given y, the P of x given y is called a posterior probability density function. Okay. So please note, why am I writing two different Bayes theorem? The first one was both are random variables. Instead of a and b, I made it into x and y. This x and y are now continuous variables, which makes it useful to us in our study of engineering inverse heat transfer. Okay, or any inverse problem, or you want to do further studies in probability and statistics. This is basically whatever you want to learn properly. There is a box, it has got 8 yellow balls, 7 14 balls. Out of that, I randomly pick up a ball, whether it is yellow or it can be yellow or blue, all that. You beat all those problems to death. and you learn also shortcuts how to solve that. All that is fine. But will it help me find out the thermal conductivity? No, I have to go to the Bayes theorem for continuous. Why do you want to find the thermal conductivity? It's very difficult to find the thermal conductivity. Therefore, I use a heat transfer principle to measure the temperature. And I know that the thermal conductivity causes the temperature distribution. I use fundas. I use my knowledge of physics, heat transfer, whatever. From that, I infer. Therefore, some yellow ball, green ball, blue ball, somebody has. Can I modify that? So, the PPDF is why is invariably the temperature of the heat flux in an inverse heat transfer problem? If y is the data vector of temperatures, T1 to T10, or it could be T1 to T1000, T100, T2000, whatever, or it could be T as various points in times at different points in space. It could be T of X, Y, Z, T. It could be T of R theta phi T. It could be anything. It could be heat flux, Q of X, Y, T, Z, T. Whatever which can be measured with an instrument. Data. This is the data science. So you get the data in the form of y. So y is the data. Y is the data which you are acquiring. Okay. This data could be either because of past data. Okay. Or you do experiments in the lab and get this data. Is it okay? So some data is available. Data. What is the data in heat transfer? The data is invariably temperature or the heat flux. Okay. So the data in applied mechanics could be the strain gauge, the strain, stress, whatever, peak stress, principal stress, root stress, circumferential stress, longitudinal stress, whatever. In different subjects, it could be seepage in groundwater. It could be runoff. It could be flood. It could be runoff. It could in hydrology. It could be voltage, open circuit voltage, this thing, whatever, current, whatever, in electrical engineering. As far as heat transfer is concerned, why is the key point? Why is what we are measuring? From what we are measuring, we are trying to find out what we are trying to ascertain the cost. X is the cost. X could be just a single cost. X could be a vector itself. X could be Kx, Kxx, Kyy, Kzz. That means thermal conductivity itself is not a single quantity. Thermal conductivity itself is a tensor, which in which case it was a thermal conductivity is tensor. Once it is a tensor, you can have basically an orthotropic material, where an orthotropic material is one which is like this: Kxx 0, 0, Kyy, Kzz 0, 0, 0, 0. This is an orthotropic material where off diagonal elements are 0. Where do these structures occur? Of course, fancy honeycomb structures which are used in satellites and so on. Otherwise, you can have xy, xz, kyx, kyz, k zx, kzy, and so on. Now, it has got six components. Now, the inverse problem, which is a really challenging, this could be a research problem, this could be a PhD problem. So, you've got a set of measurements. You're designing some fancy structure which is used in the spacecraft. Can you tell me the 6 components of this? You take whatever you want, but this is occurring in outer space. Therefore, if you're going to do the experiment in the lab, you have to simulate vacuum conditions. Under these vacuum conditions, you have to give a heat load somewhere so that some heating or cooling takes place. Under controlled conditions, remove the convection, okay, remove all other effects, measure the temperature. Can you give this x? X means you're resolving this. So it is a symmetric tensor. So this is a hard inverse problem. Please don't think that whatever is in the question paper, that is the be all and end all. Question paper is just to test how much you have studied, that's all. How much you have learned in this course. One sec. There's something which is stuck. Okay, so P of X given Y. P of X given Y is what is the probability that X caused this Y? Okay, what is the probability that this X caused this Y? What is this X? It could be anything: thermal conductivity, heat capacity, emissivity, whatever. P of X, which is here, is the prior probability density function. Okay. P of y given x is called the likelihood density function. Okay. So this is the probability of getting y's or assumed values of x. X is the royal x. X is not just one x. X could be a vector. Okay. X is the vector of whatever. It's a parameter vector. Okay. It could be rho, Cp, epsilon, k, x, k, y, k, z, whatever. Y is also a royal data vector. Y could be several y's. Okay. Now, what does it tell? Okay. If there is a single thermal conductivity, there is a slab. You measure temperatures in the slab. You don't know the thermal conductivity. You want to measure. You want to estimate the thermal conductivity. The silly stuff would be k into T2 minus T1 by x. Okay. But we are having more temperatures. Then which T1 and T2 you will change? Don't ask me, don't go back to your this thing and say, sir, k dt by dx, if I know two temperatures, I will get the thermal conductivity. It's not so simple. There is error in Q, there is error in T1, there is error in T2. Why would I want to measure only two temperatures? I will measure 200 temperatures. I'll find out the best line. I know the temperature is AX plus B. Then I'll take dt by dx. Then from that I can get K. That is the scientific, that is the engineering approach. Instead of trying to reduce and trying to say a simple problem of how to just take T2 and T1, X2 minus X. Everything is having error. We don't want to do that in engineering. Okay, so the idea of inverse problem is not to find out how we can do the you can use a basic textbook formula to solve a problem. That's not the economy is not the most important thing. I want the correct answer. I want to get to the truth. All right. So the probability that this thermal conductivity caused this set of temperatures is the product of getting these temperatures for an assumed value of thermal conductivity into any prior knowledge I already have about this thermal conductivity divided by this P of y. P of y is a normalizing constant. Therefore, it won't really affect the calculation. Okay. So now this P of x is called the prior probability density function. This means what is the knowledge you have already about the x which you are trying to recover. So that means suppose all these are Gaussian. Okay, so all these are Gaussian. The P of x will also be given as a Gaussian. That means if you are, let's say, for example, suppose you're doing a slab like this. It's a slab, and you're measuring the temperature. I want T1 to Tn. I have measured. Okay. Now the goal is all the temperatures I've measured errors, and I have many more temperatures. I can't just use T2 minus T1 by T3. But if I use multiple pairs, I will get different values of thermal conductivity. Then I don't know which one is the correct answer. Therefore, I have to choose the best. Now, this is a classic inverse problem. Okay. Now, K is my unknown. The P of K, the P of X is actually the P of K. Huh? That means if I am smart, if I am a good engineer, then I will say I will construct what is called a prior. So this is having a mu and a sigma. Suppose I know it is belonging to a steel family, I may give mu to be around 15 watt per meter per Kelvin. And the sigma could be 10% of mu, 15% of mu. That is left to me. How do I know it is 15 watt per meter per Kelvin? I don't know. I could be wrong also. But this comes from my prior knowledge. It looks like a metal. It looks like this thing. Therefore, I give it a guess or a prior guess. Therefore, the P of X is something which is subjective. Therefore, all the people who are solving the Bayesian, even if you give them the same data, the same forward model, they will not get the final answer. Then, in mathematics, there should be JEE, whatever, everybody, there should be only one answer. Why should everybody get the same answer? The smart fellow will get an answer which is better. Who is the smart fellow? The smart fellow is somebody who already knows the subject, who has a domain knowledge. That is why classic mathematicians opposed the Bayesian for a long time. The Bayesian was not accepted, but now Bayesian is an integral part. In fact, the Bayesian regularization is very much a part of the training in any neural network. Go to the MATLAB toolbox, you can see something called Bayesian regularization. Therefore, the construction of the PX of the prior is an art. Okay, we can use many scientific methods for creating the P of X for various kinds of situations. The P of X is only a data vector. The P of X itself could be X could be consisting of X1, X2, X3, X up to Xn. Therefore, the whole game of the Bayesian lies in this prior. What is prior then finally? What is prior? What is it? The prior is nothing but a quantification of beliefs. You can take several avatars. You can take several. One be that I search only in I search. I do an exhaustive search. I don't do all this. I do an exhaustive search, but I do in an interval. This exponent, I don't search for thermal conductivity from 0 to infinity. That only a mathematician will do. Why should I search from 0 to infinity? Which is that material which has infinite thermal conductivity? Which is that material which has 0 thermal conductivity? Why should I do 10 to the power of -7 to 10 to the power of +9? There is no thermal conductivity more than copper or steel, gold or something. What is the point in doing 10,000 or 100,000 just because mathematically you can do it? Is there any material which is like that? There is no material. Therefore, the smartness lies in reducing your bounds. So this is bounds, giving bounds, or giving a distribution. Giving a distribution. So you can do a lot of things with the prior. So this is a Gaussian distribution. You can do a Weibull distribution. You can do a Poisson distribution. You can do a binomial distribution. So then you have to go deeper and deeper into probability and statistics. So there are a lot of people who are working on priors, Bayes, and all that. These are mostly applied statisticians. It doesn't come in pure mathematics. So you can look up the website of ISI India. Okay, ISI, don't get it, not Interstate Intelligence, Indian Statistical Institute. They have Calcutta and branches in Bangalore and so on. There are people who work on Bayesian. Okay, so a person who believes in all this, that a belief can, if you quantify the belief and put it into the system, then it can do magic. Then you are a Bayesian. Okay, the person who is doing that is a Bayesian. Now, this likelihood is what? Okay, in this case, let us say T1, T2 data. Let's say from this K, you're getting T1, T2 simulated. Okay, sigma I equal to 1 to n, Pi data minus Pi simulated whole square. Okay, this is your S. Okay, now this is your, you can do it by sigma square, whatever you want, call it a square. Now you can say that P of I given X. What is that? All right. Did I make any mistake? Is it okay? So what you do is a simple slab problem if you want to solve. Simple slab problem. You got T1 to Tn. What you do is first you will assume a value of k. Once you assume a value of k, you will solve the forward model. It's a heat conduction problem. Then it will generate, you can generate T1 to Tn simulated. Then you know what is the data, you've got measurement. Take the difference, square it, and you can. So this is the sigma square is the error associated with the measurement plus the forward model. This is usually known to you. Okay. And calculate the chi-square, and you can find out what is the probability of P of y given x, or P of probability of this y given this particular k. Okay, this particular value of k. Now what you do is P of k given y is P of y given k multiplied by any P of this thing you already have. Now if you keep on changing the value of k, you will get a distribution like this. Okay, this is P of y given k divided by k. Suppose you are guessing a value of k which is actually close to the truth, then the kappa square will be very low. Therefore, e to the power of minus kappa square will be very high. That is likely to give you the maximum probability of this distribution. And now you are putting your own jam. You have your pandas. You are putting a P of k versus k. Now the product of these two Gaussians, assuming that it's a Gaussian, the product of two Gaussians will be a Gaussian. Therefore, the P of k given y will be another Gaussian. Please note that this is your posterior probability density function, or the PPDF. This is basically P of k given y for a particular value of k. Please note that the Bayesian combines everything. The Bayesian lies not only at the root of engineering, it lies at the root of life. Because you see this, if you want to get to the problem, if you want to know what the truth is, the truth in this problem is the thermal conductivity. If you want to know the truth, you want to approach truth, you have some beliefs about this. Then you do a mathematical model because your physics, whatever learned, your calculus, whatever you do, whatever you want, do this. Then you make a measurement and get the temperature data. Get the difference between these two and put it as your likelihood density function. Multiply it by the prior. Then get this. Now nobody will tell you that is the answer. So the beauty of this approach is the Bayesian approach. Finally, the answer is also given as a probability. Therefore, there is no wrong answer. There is no incorrect answer, so to speak. What do you mean by that? It's a loaded statement. What I meant was, any thermal conductivity could be a solution to the problem, but any thermal conductivity, you are not saying this is the answer, this is not the answer. You are quantifying it in terms of a probability. Everything is put in terms of a probability. Your belief is put in terms of probability. Your likelihood is put in terms of probability. Finally, the answer is also put in terms of probability. Therefore, if 15 watts per meter per Kelvin is what the thermal conductivity of finally the object or the material which originally caused these temperatures, even a thermal conductivity of 0.01 will give a probability, but the probability will be very low. Likewise, if you assume a thermal conductivity of 800 watts per meter per Kelvin, that will also give a probability which will be very low. However, when you're searching for the probability in the vicinity of your 15 watt per meter per Kelvin, either at 14 or 14.5, 15.5, it will be very close to the peak of the curve. Therefore, finally, it will give you a distribution. You are free to proceed further with this distribution. The Bayesian stops here. Now, you'll have to post-process this distribution and you have to use estimators. What are the classic estimators? One could be, you can find out what is the value of k at which this hits the peak. Okay, that is called maximum a posteriori. So you will look at point estimate. Maximum of PPDF. Okay, is called MAP. Maximum a posteriori. What is the value of your k or your x at which the probability? I'm very much into this, so I don't know what where I left. I forgot what I said. Okay, doesn't matter. All right. Now, so this is the This is the heart and soul of the Bayesian method. Now we'll solve some simple problems. To start with, so what should be the problem number? Suraj, can you just show the problem sheet? I'll allow you to share.
Yes, sir. Yes.
Okay, please do that. It will be 16, 17, and it will be 16, 17, and 18. So let's do only the 16 and 17. So the electronics plant, please take down this problem. At an electronics plant, it is known from past experience that the probability is 0.86. That a new worker who attended the training program will meet the production quota. The corresponding probability is 0.35 for a new worker who did not attend the company's training program. If 80% of all new workers attend the training program, what is the probability that a new worker will meet the production criteria? Please read the problem, copy it down, and we'll solve it. We'll solve 1 and 2. I'll ask Suraj to post it on WhatsApp. So the third one you can complete on your own. And then whatever we did, that slab problem, we are going to go deep into the slab problem. We'll take some data from the past problem and solve it in Wednesday's class. It will be fun. Thursday, I will tell you how to do it using the Markov chain Monte Carlo method. So, but we'll restrict our attention to a single variable problem. That's enough. Once you know what is for a single variable, you can learn from outside. You can learn from other sources how to do it for a multi-variable problem, multi-parameter problem. Okay. So, please try. In the interest of time, I think we just use the last year's problem because this course itself is new, right? I think we developed the problem. Suraj, we developed the problems only last year, right?
Yes, sir.
Okay. I want to write a textbook. So I'm just trying. So we didn't want to create new problems. Now we'll just see that whether everybody is able to pick up. Me and S. Balaji, we are trying to write this book sometime this year. Let's see. By 2022, we should be done. There's no book on the subject from Indian region, and this style is not there with many problems and all that. So maybe there's some space for us to contribute. If somebody is willing to play game with me, play ball, I'll just start writing. Or somebody wants the video to turn on their video and then lead the class, it's fine. Anybody, any volunteer? They are not tough problem, simple problem. Anybody wants to do that? You can post the answer on the this thing also. You can post the answer in the chat box also. Suraj, did you call Rajesh?
Yes, sir. I called.
What did he say?
Coming, sir, within 5 minutes.
But 10 minutes class will get over.
Yes, I will come, sir.
Okay. Now, in the interest of time, let me start solving the problem. Is the problem clear to you? Somebody should tell me. I'm not able to see you people. I'm able to see only the sheet. Subhash, Gautam, is it clear?
Yes.
Problem is clear. Very good. Okay. Now, okay. So these. Okay. Probability that a worker attended training. P of T is 80%. Okay. Probability that a person who attended training and satisfies the production criterion is a conditional probability. He attends the training and he has benefited and he is satisfying whatever we want. This point is. Sai Pavan.
Sir.
Now can you see that P of T and P of P are independent events?
Yes, sir.
Okay. Now, what is the question? I don't even know the question. Okay. What the probability that somebody is a genius, he doesn't attend the training, no training, but still is satisfied. 1/3 of the people are doing that. They are stud guys. But there are some 14% of the guys who will do the training and still they will come. You understand? So all sorts of people are there. Worker meets production criteria. Whatever. This is what our goal. Huh? Probability. So this can come from two ways. By taking courses, writing exams and all that. Some geniuses, no training. Correct? Both fellows are there. So here, okay. Here it is 0.8 into 0.86. 80% of the people are trained, out of that 86%. Here, 20% of the people are not trained. Out of that 0.35 fellows are already satisfying the fellow. This is but now we have to add these two because from both the sources, the worker who meets the production criteria can come from the training background, can also come from the non-training background. But from the non-training background, the probability is only 7%. But once it is trained, it is on 68.8%. Okay. Now total probabilities. They are independent. So you add them. Okay. Total probability is 0.758. Is that okay? As far as the company is concerned, they are happy. 76% of the workers will satisfy this. Okay. Then you will have to do analysis. The managers will do analysis and find out which has to be improved. Okay. So the efficacy of the training, or more people should be, what is that? Or more people should be trained, whatever. How to control the COVID, whether more people should be vaccinated or more COVID appropriate behavior, or more testing, or more isolation. So these are all, there are many strategies. So all there is some probabilities going on. So some Bayesian is at work there also, right? Okay. They will work out a truth table. Okay. Yes, yes, no, no kind of things. Okay. What is the probability that somebody who is vaccinated will get corona? What is the probability if someone is not vaccinated will get the probability vaccinated and social distancing getting corona, vaccinated and social distancing not getting. So there could be multiple combinations possible. Okay, so there Bayesian will be at work there. Any doubts in this? Is it fine? You just say somebody can tell me fine.
Yes, sir.
Very good. Okay. Now let us go to the next one. Just hang on for a few minutes. We'll complete this problem so that we are woefully short of time. Okay. So I have only 2 more classes, and you saw that already. I took half an hour. I just went almost into the board because basically we have done a lot of original work on Bayesian, and we have published a lot of papers. You can just Google up the Science Direct and so Bayesian. So I'm a Bayesian. Okay. Now I strongly believe in Bayesian. Okay. So That is why I thought I would spend only 5 minutes. I think I went deep and got carried away maybe. So problem number 17. I want to do 3 problems, but it's okay. What is that? Some tire company is there. A consulting firm rents cars from 3 agencies, not tire company. So there are, okay, Ola, Uber, whatever like that. You have 20% from agency, 20% agency B, 20% from agency F, and 60% from agency F. Sorry, D, E, F. So total is 100%. Okay. However, 10% of the cars from D, 12% of the cars from E, and 4% of the cars from F have bad tires. Very bad tires. It's not good customer complaint, whatever. What is the probability that the firm will get a car with bad tires? This is a probability you want to work out. Okay, if you are in that consulting firm, you want to know this. Okay, so we have to do this. Probability of renting from company D is 0.2. Probability of renting from E is 0.2. Probability of, so in order to save time, I will say prob of renting. Okay. Probability of getting a bad tire from D is 0.1. Probability of getting a bad tire from E is 0.12. Probability of getting a bad tire from F is. So this is conditional. Huh? Please note it is a conditional probability. Conditional probability of probability of getting a bad tire is 1. Probability of getting a bad tire from that company is a conditional. It's a condition. You are putting a condition. That's why it's a conditional probability. Okay. So probability of getting bad tire is very simple. Probability of getting bad tire from B multiply how much you are renting. E plus probability of bad tire from E into probability of E plus probability of getting a bad tire from F multiplied by probability of hiring. Please do that. So how much is it? Point 0.1 into 0.1 into 0.2 plus 0.12 into 0.2 plus 0.02 into 0.6. Is that okay? Oh. About 7% of the tires are bad. Is it okay? Now, the last question is, correct. Somebody says correct. Who was that? Okay, the last one. What is the probability that the car with bad tires came from agency F? That is this one. Okay, probability of the bad tire coming from F. Okay, that is what is that? Great. So Anand, very good. So funda is there is a 35% chance that the culprit is agency F. Like that, you can find out who is the culprit for the other things also. Okay. So the third problem is also fun. Some corrosion in pipe or something. Suraj.
Sir.
Suraj,
Yes, sir.
just send only the problems and not the solution to the student by WhatsApp. Now it's
Okay.
okay. So thank you very much. Suraj, get ready for this slab problem. So I will demonstrate it, but then all these tables and other things you have to work out. Okay.
Okay.
Next class Wednesday will be heavy. Heavy calculations will be there. Okay. So please come prepared with your calculator. So we'll complete the Bayesian. One problem I'll show you how to solve the Bayesian single variable problem. And then once you understand, once you figure out, then it's very easy for you to do. So particularly people who want to do projects in this, or they are in interdisciplinary data science program, who want to do data science. If you have a good hang of Bayesian, you can do wonders with data. Okay, so the whole philosophy is how to marry data with forward model with belief. That's all. Life is only about that, right? So if you observe certain things, there is some hypothesis, there is a belief. How do you mix and match all these to have a nice outcome? That is what we are also trying in inverse problem. That is what we are trying in life itself, to understand, improve, whatever, and go forward. Thank you very much. I hope this class was interesting, because today's class is the basis for which I started this course. All the things which you have learned so far is basically to get you to this point. So this last week is the most important week. So I started with Bayesian 2007, 2008 with some 2 BTech students. So after 13 years of work, it is Bayesian which motivated me to start an inverse course. Because the traditional inverse books, you can take any inverse book from the library if you want to e-copy. If you get an e-copy, nobody would have talked about the Bayesian, because the number of Bayesians in heat transfer is very less in the world. So we are one of the few groups here aggressively promoting Bayesian. Okay. Initially there was resistance, but now they know that our group is doing a lot of work on Bayesian. So today's class is the main motivation for me to offer a course. It is running for the 3rd year. Every year we have got 100 students in this course. All right. So long live Bayesian. All right. So I'll end the class. It's absolute fun. I mean, it's a stud. I mean, the Bayesian concept is actually not because I am doing it. Whatever you just think about it. It combines everything. It's just a thing of a beauty. Huh? So let's end the meeting for all. I'm getting a call. Bye.